Hello everyone, assalamu alaikum, and welcome to another session from the DevMena team. Thank you, Leila. Uh, I think I can hear myself. Um, Let me see. I think I was I opened the YouTube video. What am I saying? So hello everyone, welcome to another session from Dev Mena. Two sessions. Thank you very much, Leila and the team for actually hosting me in this session. Today we're gonna go through a workshop or a step-by-step workshop on how you can actually train a GPT model, just like a mini GPT model on your own text. Let's like how to pre-train it from scratch using casual learning and just Flax using the new library from Flax NNX. If you're not familiar with me, it's me, Bouhsين. I'm an AI GDE, a Google Developer Expert, and the CEO of ML Nomads. And I am a research scientist too, in my own company. I'm just trying to do research on foundational research on an AI and stuff like that. I created I'm doing white box neural networks, if you're familiar with that term, where we are trying to create neural networks without the need of activation functions. Besides all of that, today we will focus mainly on just how to train a mini GPT model using Flax NX on a TPU from Kaggle. Let's start first by just going through some actually, just some few, some few topics that we need to talk about before actually starting the GPT, which is just casual learning or masking versus regular mask. So basically, when you are trying to train a neural network, you have two times for attention. So you have some few ways you can actually um, construct your own attention mechanism. So if you are familiar with the BERT method, just when you are trying to use kind of the whole context. So basically, your model or your attention mechanism allowed each word to access all the words in front of it, as well as access all the words behind it. It does not limit the word from accessing any information it needs. It just kind of try to give it the ability to see what's in front of it. It's kind of like bi-directional connection between the words in the whole sentence. But when you are using, this is the fully visible one. This is the one that is used by kind of the attention, by most of the original attention. The original attention is going to need paper. And then there is the other one, which is the casual learning. And here you have each word, this is the X1, this is the first word, is only able to see the words behind it. For example, if we are in X2, we are only able to see the word behind us, not the words in front of us. All the words in front of us are hidden from us, so we cannot actually access that information. We cannot attend that information that this word holds. And this is the main method that is used to train a GPT model, where you are trying to actually give your model the ability just to only rely on the information of the previous words to actually do the next token prediction. Um, Both of these methods are very useful. For example, if you are interested in learning about what is the real meaning of the whole sentence, you will tend to actually focus more on the fully visible attention, since you are interested in building a model that understands the whole sentence. But if you are building a model that is next token prediction, you don't care that much about what's in front of a word, as much as you care about what's the word that is going to get predicted. And then there is the casual with prefix. It's kind of similar to T5, to T5 model, if you are familiar with that, where they will just give an action, or give a prefix to the model first, and then they will ask him to predict the rest of the sentence. It's the method used for translation, where you will just ask the model translate this phrase from English to French, and then you give him the phrase, and then the prediction that, or the model should start predicting not from the sentence or like the sentences like or the words that you gave him, but from right after the end of that sentence. So basically, like he will just like start predicting directly from here, where he will just like start predicting. So the whole x1 and x2 and x3, we will not use any prediction. We will only use the prediction of the y4 and x4, just like for doing actually the loss calculation. There's this, and then there's like actually GPT-2 mall architecture. So in the GPT-2 mall architecture, there is like a bit of difference compared to the usual attention. Um, in the um, in the usual attention mechanism, you have like both the encoder and then the decoder. This is like the usual transformer. You have the encoder that takes the sentence and encode it, and then you will use that information or the information from key and values to actually merge it or just like fuse it with the information coming from the outputs, which kind of like help you with the prediction of the next token. But um, it's kind of decoupled. The input that you gave it is different than the output that you gave it. And then you will have your own output here as a software. But in the GPT architecture, you basically remove the need for um, you remove the need for like I would say like an encoder. So it's called a decoder only architecture, where you are just like passing your input. Like you have a sentence, you will just like tokenize that sentence, and then you will take each token from each word, and then you will go to the input embedding and just like take the words or take the vectors that are corresponding to those vectors, and then you will add the positional encoding, and then just like you will do the normal attention, which is just like dropouts and then transformer block, transformer block, transformer block. And this is like the content of the transformer block. So basically you have a layer normalization at the beginning. You have a skip connection that we will use layer. And then you will do a linear, just like a linear with multiple heads. And then you will combine all those multiple heads into another linear to actually just like do the dimensional reduction. And then you will drop out. And then this is the MLP block of the attention block, where you will just like expand the dimensions of your input or of your vector and just like try to project it in a higher dimensional space. And then you will just like do again the dimensionality reduction using another linear, and then you will drop out. And then you will continue, will give this output to the next block until you reach the softmax. This architecture is easy to train compared to the encoder decoder model, where you will need to actually just like pass the inputs, and you cannot like merge between the masks of both the inputs and the outputs like later on. So this was the main architecture that actually started the GPT-2 model, the GPT-2 models from OpenAI, and it was actually like one of the actually good use cases of like how to use transformers for large scale pre-training and stuff like that. And today we are gonna see like how to do like training from scratch, just like on a simple like use case. So basically, let's just like let's first start like our server, and then we can continue. And now let's go to just like Kaggle. If you're not familiar with Kaggle, this is a platform where you can do a lot of fun stuff. You will learn from people doing like modeling. You will find like a lot of models, a lot of data sets, and a lot of competitions to actually participate in. And you will also find the discussions of different people talking about some topics that just like reading these things will help you out to actually build a better understanding of what you need to learn and stuff like that. But for us, we'll just like create a new notebook. You will just like go and click and create a new notebook. And then you will go to the accelerators, and then you will choose the TPU V3. Um, Basically, the Kaggle provide you with like 20 hours for free each week, and then during or at the start of each week, it will reset the whole 20 hours if you use anything. The TPUs are the main competitors of GPUs. They are like a compute kind of like that is created by Google, and it's kind of performing well, and you can actually scale large models easily on top of it. and especially if you are using like JAX or TensorFlow, but mainly JAX, you can actually pre-train your models faster and without actually losing that much computing time. So the price to train it, to create it, is really low. So let's just like turn on the TPU, and let's just wait. I think let's just like start the session. If you click on this button, you can actually start the session. Ah, that's cool, 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 cool. So basically, let's go and install some of the like some of the actual libraries that we will need, and we will need also to update, just like to install some, to remove the TensorFlow GPU, so it will not create any problems for us. So I will go and take that import from one of the notebooks that I created, but don't worry about it. I will share everything with you later. You will find it in this notebook. So okay. So now we can actually go here. Like this is one of the fun things that we can do is we can go to server to run. You can go to run, and then we can just like start a Kaggle Jupyter server. So this we'll just like take this link here, and then we'll go back to Bash Nota to actually use it. So we'll just like go to this icon and then remove this one from the before, and then from URL you can do this, and it's just like Kaggle GPU, pass URL, add server, and now we have a server we can use for our code. We click on this button so we can connect, and then we can just like use a code block here, and then we can start actually all fun. So the first thing first, like we need to do an install of the whole, not this one. Where's the Kaggle notebook? So this one. So we need just like to install some of the libraries. We need Tyrone weights and biases and stuff like that. We need JAX, and we need JAX CPU, not JAX GPU, but JAX CPU. And if you are planning to use JAX CPU, you need to kind of like make sure that your TensorFlow library is on CPU, working on CPU, not on the TPU, so there will not be any conflict. And then there is like the latest updates from Optax, just like to kind of like have a good, um, just like a good trainer and stuff like that. But we don't need it. If we need it, we'll add it later. So basically, let's click on run. Okay, I think it's done. Yeah, it's done. So let's just like do another code, and then actually go back actually to the Kaggle notebook here. And now you need to do something here. You need to go to weights and biases, and you need to try, or I'm not sure if we need it, but let's just like do it. Log in to weights and biases. So this is a cool platform if you are planning to actually track the loss function in real time, if you are trying to see how like different things are working and stuff like that. So basically, we can actually just like you can actually view a lot of stuff here. You can actually also do like you can upload your own images if you are trying to train like and like if you are interested in doing like graphs and stuff like that. If you are interested in uploading your own like scatter plots, you can do it just from here. Which is a bit like it helps a lot when you are trying to do the analysis of different loss. For example, if I'm trying to compare different models that I created here, like based on uniformity and stuff like that, you can actually do that. You can also do, I'm not sure if I did it, but let's see. Oh no, I did not do it. But you can basically just like upload any image you want and stuff like that. So you need to go here and just like you need to kind of get one of the keys from your account. You just like click on API key and just like try to copy this one. And then you will go back to your Kaggle notebook and click on add-ons and just like add it as a weights and biases key. So now once you add it, once you add it like from here, you can just like enter it and then you can insert the label and you can just like it will appear. And then once you activated it for this notebook, you can actually access it anytime you want. So let's start actually. Let's first do something. I'm doing like just some copy and paste of some codes that I already created, so just like we don't actually have any problem later. I think we received an error at the end of this. Let's see what is the error. No, there's no error, just like roots. Okay, a pipe version. Okay. So let's just like run this one to see like how many devices we have. If you are using a single GPU, the result of this script will just like show you one actually GPU. But since we are using the JAX, we can see like that we have 8 TPU devices, so we can actually run our training on parallel devices instead of a single device, which makes like it will help you actually uh, get more batch size and also like train larger models without needing actually to buy any GPUs and stuff like that, multiple GPUs. And the training of like on single GPU is a bit like I would say easy to train, but when you are doing like training on parallel devices, it kind of get a bit complicated since you don't know. Sometimes if you only have like one, like some data duplicates, some images that are duplicated in your data set, and you gave it in the same mini batches, you gave it to multiple TPUs, and then you combine that, it will just like kind of overfit that specific image. And so you need to make sure that your data set does not contain any duplicates. It does not contain any bad examples or anything like that. And you need to make sure that for in your script, you need to make sure that there is no actually data leaks like between the training and the validation and all that stuff, just to make sure that your training is actually correct and not actually just like something else. And sometimes like you think that your training is going good, but since like you don't have enough data, you will just like be overfitting that data set. So for this example, we will be using tiny stories from Hugging Face. So we just like download it using wget, so just like a command line interface, and then we will put it in this file here. So we just like launch this so we can actually download it. You can use any text file if you want to train your model. You can just like replace this with any text file that you have, and then the whole code will still run without any problem. It's already downloaded and saved. We can actually just like check it. Code. We can just like do. So let's just like do ls. Let's see what are the files that we have in. Yeah, so we already like have it in the local machine. So now let's just like go and actually start our code. So we will use PyGrain for this one. We will use like PyGrain for actually downloading, like for downloading or for loading the datasets. It's like similar to Torch datasets and also similar to TensorFlow datasets. It helps you like load files and it helps you prepare them beforehand. And for the tick token, we will use it to load the GPT-2 tokenizer, so we can actually tokenize our sentences using the byte pair tokens. So let's just like run this. It's not gonna take us a lot, and it's just like it helps you actually just like to load the codes and everything. So let's just like do this, and then let's just do code, and then it's just like load the tokenizer, and then we need to do first of all we need to do like the casual masking, if you remember. We need to create like the casual mask. So here we are using Trill. Um, Trill actually help you create a triangular mask for your own like just like a triangular matrix. If you are familiar with the linear algebra, it will just like help you create a triangular matrix, and then the rest are filled with zeros. And we are filling the triangular matrix just like we are kind of trying to trim this ones with just like the gnp.trel. And then by using this function, we can actually create the mask here that we talked about. This mask here, the casual mask, since it's just like a triangular matrix, like the rest are zeros, and then the top is just ones. Just like what are, oh no, the top is zeros and then the rest is one, so we know which information should we mask and which information should we keep. Then we will just like create a transformer block. We will use this. It's just like typical transformer that we've seen like in previous sessions. So basically, you will just like do the normal attention, which is just like we are using Flax NNX. It's like almost similar to the Torch framework, but it's like using JAX in the backend. We have like instead of using, if you are familiar with Flax Linen, you used to use like linen.model. Now you can use just like nnx.model. And if you check the just like the logic behind everything here, you can see that it's just like it's almost like similar to like how we usually actually do just the how we use actually just like Torch, if you are familiar with that. And let's just do this actually. Okay, let's just like kind of format it better, so it will help us actually look, understand things, how things are working. And then this is the same thing for the linear. Okay, so we in NNX, in Torch or in Keras and TensorFlow, we used to use dense, but they just like switched the name into linear. And then for this linear, you can actually just like have you can specify what is the dimensions of the inputs and what is the dimension of the output. Usually in Flax, in dense, and also like in Keras, usually you don't set the N features. You are only caring about the out features, and Keras actually calculates the N features dimensions for you, and then use it to actually calculate the matrix. But like in Flax, they actually change from, or the in NNX they change from away from that, so they can, you need to specify your whole dimension. So you will be in control of what is the dimension of your own like if your own weight matrix. And if there's like an error like of misdimensions, you will get the error clearly without actually like kind of being lost in the middle of everything. So we have, like, if you remember like our architecture, we have the first linear, which is like the one that is used for attention heads, the second linear, and then the third and fourth linear. And if we check the code here, we can find like just a few of them. They removed some, I think, attentions. So this is the first layer, which is the linear normalization, and then there is like this is the first linear, and this is the second linear, and then there is like the other linear. Wait, let me check. Yes, so like this is the one used for actually the feed forward linear, and this is the one that is used for the attention head. Yes. So this is the MHA. Oh no, the MHA already contains like the whole in the MHA. Let me just do this. Okay, so in the multi-head attention, they already like use the block from multi-head attention that contains both both this linear and the other linear. So we are cool. And then we have the layer normalization. This is the first layer from the linear block, from the MLP block, and this is the second layer. And then at the end, there is like one big layer. And then we use this function that we created earlier here, the casual mask, casual attention mask, to create like a casual masks for this actually for our input. And then we will use this mask to actually mask the attention, or provided it to the MHA, to the multi-head attention, so we can actually just like trim or remove some parts of the attentions that we calculate. And then we get the output of this, like the output of the attention, like the output from the input that we gave it, and then it will just like provide us with an output, which is the attention output. And then we'll just like drop out the attention if we specify that we need to do the attention dropout. And then you will do the skip connection here. This is the skip connection between the previous input that we had and the attention outputs. And then you will provide this out to the linear relu, linear dropout, and then you will return the another skip connection between the out one, which is this one that we just calculated out of the attention layer, and then we added it to the FF output, FFN output. So here you can, this layer here is like is gonna just like do the dimensionality augmentation, and then this layer here will do the transformation, the linear transformation back to the original dimension that we have. And then we will just like use this attention block or this transformer block to actually build our model. So let's first like run the model. And let's just like take another actually block that we are interested in, which is the positional encoding. There are different types of positional encoding. Some of them just like some of them use something like similar to a vocabulary of positions. You will just like use another kind of like embedding instead of using a sine or a cosine to actually do the position and encoding. You will just like use a learnable token to actually do the tokenization. So here, if you are using this embedding, like this embedded layer, you are a bit like limited to the number of if you want to do the augmentation of your context, you will need to also do the augmentation of this embedded layer, and then you will need to do a bit of fine tuning for it. So which is a bit it will take you a bit of time compared to when you are using the sine or cosine. But this one provides you with a learnable positional embedding, not some embedding that is like just like fixed for everything, but it helps you create a learnable positional embedding. And then this is the vocabulary that we have, like this embedding here. We will use it like as a vocabulary for the rest of the tokens to actually access to associate each token ID with a vector in space. Then we will use it to like when we get a new input, like a token input, we will just like take the tokens that we have, and then we will just like take that token and then just like get it from the token embedding, and then we will just like do kind of like an addition between the positional embedding and the token embedding, which is kind of like just like doing positional embedding for the neuron. So let's just like run this code, and then we can now create our own mini GPT, I would say. But let's just like say something. Let's do something first. Okay. Okay, so let's just like do another code. And now let's do this like GPT. Let's just like go through the implementation one step at a time. So like the mini GPT takes like this is our model that we will use to actually, this is the model definition that we would use. We're gonna use all the methods that we created earlier to actually define the GPT. The first method, which is, or the first like element, which is the init again. Here you are creating an embedded layer that takes care both of or that takes care of like both the embedding, or just like kind of doing the embedding, just like the taking a token or taking an ID and just like getting the embedding from the embedded layer, as well as the positional embedding that we created earlier. So it will use this layer to actually take care of everything, like for this specific part of the transformer. And then we create a list of transformer blocks that allows us to actually that allows us like just this is like the transformer blocks that we have. And then this is the output layer, which is the layer that we use for actually using for that we will feed to the softmax. Some people actually like instead of or some in some architectures, instead of using a linear layer, they will use just like the original vocabulary size, the original embedding, and then they will add it to they will add it again to the just like they will take that embedding and use it as a kernel, or like as a weight matrix to actually do the forward or the output prediction. Um, but sometimes that a bit that like kind of like limits you actually just like to the space that we had originally, and you will need to always kind of try to control your outputs, or your like your embedding vectors, or the vectors that you are trying to predict, so they will not go out of that latent space, or out of that kind of range between 0 and 1. For example, if you are limiting the embedding to just like 0 and 1. So, but when you are using the NNX delta linear, it gets a bit like you are more flexible, I would say, compared to the previous one. And so, like the output layer is just like a linear, similar to the other output, the other layers, and it takes us like the in feature is just like the embedding dimension from each of those vectors that we have in the attention layer, and the output vector is the number of words that we have or the number of tokens that we have in the vocabulary size. So we would use vocab size for the out features. And then this is like just like the initializer and some stuff like that, the shredding for the model and stuff like that. Just like we can actually provide it to the TPU. For the call, you will just like call the embedded layer, and then you will call the block on each of those inputs until you reach the output layer. Let me just like first the output layer, and then you will call the output layer to do the final layer, and just like return the outputs here. So and then you can do the softmax on top of them, or you can do just like the top K on the logits if you want. This is the main function that you will use if you want to test your model to see like how good it is, like just like to see if you are trying to do like a softmax on top of it or something like that. There is like instead of doing the softmax on the whole 50K of attention for of the output layer, basically what they usually do is like they will take only the top K indices of the output of your logits, and then do the softmax, since it's less expensive that way compared to when you are doing the softmax on all the models, on all the vector or all the whole vocabulary size that you have. And this is exactly what's happening here. You will get the logits and also the indices of those logits. And then using this top K would that only provide you with the top. For example, if we specified K as or top K as 100, it will only provide you with the logits from the top 100 like scalars from your vector, and as well as the indices of those like scalars. And then you will do the logits or the softmax on top of those logits, and then you would take this random choice, and then you will do the sampling from those logits that we created here using the indices that we selected, and then you can actually just like select the element that are the word that is like that has the highest similarity with your attention or the attention outputs, and then you can just like do the next word protection. And the generate step is taking the same it's taking a bit of it helps you actually just like generates one token at a time, and then actually just like return it again to generate the next token, and then just like to help you actually just like extract which index that you are trying to predict next, since like the whole like the transformer block or the final layer will predict like a vocab size of tokens like as the whole thing, but you need to remember which token you are trying to attend to. You should not like just do the forward pass for everything, but you should just like remember which token that you are trying to attend to, and then once you find that word, you will return it again to the model, and then you will do the forward propagation. And this is the autoregressive part of it, especially during this like the prediction. You need to predict one word at a time, and this is like one of the kind of like main motivations on why people are moving towards like diffusion language models instead of instead of this type of like modeling, which is the casual learning. And here you will just like do a for loop to actually generate one token at a time, and then until you reach the end of the sentence, or until you reach the end of the number of tokens that you have. So let's run this. I talked so much and I did not run anything. Let's just like run this, and then we can just like have a function. We can have just like a function that allows you to do so this is a function that allows you to create a model, uses the RNG keys that you provided. Just like it will use just like 4 transformer blocks for now, but later on you can actually just like change it using the hyperparameters if you are interested in that. And now let's just do a code and then define the vocabulary size. So we are gonna use the tokenizer from GPT-2. GPT-2 tokenizer have like around I think 50K of tokens in the vocabulary size. We will use 8 transformer blocks. We will use the max length of like for the next token prediction, we only use context window of 256. The embedding dimension is 256. The number of heads is 8. The embedding dimension should always be divisible by the number of heads, and then the feed forward dimension should always like be a bit similar to this dimension here. And for the batch size, we can actually just like use 256 since we are training on a TPU. But like we can actually increase it if we want to. Let's do it like let's keep it 255 for now, and we can do like for example one actually epoch, and then we can actually use this to actually um just load the just to actually define the model later. Now this is the where the fun part is. So let's just like do data. Then so this is like everything here is just like the GPT-2 model. So let's just like do something like we can just like take. Oh, we'll do it later. I will do it later. So we can just like do here code. So in for the data processing, we are gonna use a bit of different actually library. This is a new library from DeepMind. Um, it's compatible with the shredding and everything. It take care of the shredding and all of that stuff for you, and it's somewhat similar to how Torch datasets works. You have you define your own, just like your class. It's a data class that has a length, and then it has a get item. This get item is automatically called when you are trying to do a for loop on the dataset. So it will just this get item will take the tokenizer that we have and tokenize the data or the index or just the phrase that we gave it, and then it will just add a token at the end, which is end of text token and stuff like that. And then we are just trying to figure to see like if this we we need to kind of create a pattern. Like if so, let's say our context window is 500 and 512 512 words, but our phrase is only 128 words. So we need to pad for each word of those they have an index, but for the rest of the tokens, do you need to be just set to 0, just like a pattern, so we can actually feed it to the model. And then there's the load and process. This will load just like the text file, and then it will split them using this token here, so you can actually split each phrase from the rest of the phrases, and it will just create a data frame, a pandas data frame that actually associates text with a story, and then you can actually just remove any none or anything like that, and then you can just create a data set using this actually data frame here. Then you will just create a sampler, or just a PyGrain sampler, which actually you will give it the index of or the length of the data set, how many phrases you have, and then you will give it a seed, and then you will kind of say tell your model or tell your actually your for loop this is this is not gonna we are not gonna shred it yet. And then you can create using this sampler here, you can create a data loader that actually load this data set using the sampler that you just created. There are different types of samplers. Just check the documentation and to learn more about the difference between those samplers. And then you will use the PyGrain batchers to actually batch the data sets according to your own according to your own batch size, and also to drop any reminder if there's some batches that don't have enough data and stuff like that, and then you can return it. And then we can use this function to load our own file and prepare it for us. So let's just run this code and see how it goes. Yes, I think it ended everything. Now let's just do another H2, so we can actually do, let's say, name phase, and then we can just create a code, and then we will define the loss function. This is the first thing. So the loss function is just like taking the model that we have, the model that is created using Flax NNX, and the batch size and the batch, and then we will use this loss function to actually calculate or just like generate the logits, and then we will take these logits and then provide them to Optax, like to the softmax, like a loss function by Optax, where that takes the logits and the indices of the labels, not actually a one-hot encoded labels, but just like the index of each word, and then it will just like transform these labels if you check the code of it, it will transform these like using an optimized, or it will calculate this loss using an optimized loss calculation or a softmax calculation, a cross entropy, softmax cross entropy method that does not need to transform these into one hot encoded vectors. And then it will just like return the loss and the logits. And then the training step is using nnx.jet. So actually, I jetted everything like or it's just like it's just in time compilation where it will just like compile this function at the first time, and then the next time you don't need to compile this function again. You will just like use the previous compiled functions that you created, and the code that you put in this here, you need to be using need to kind of follow the principles of functional programming, so you will not have any leaking or any shared values from inside with the outside world, or the outside actually scripts. All the functions, just like read about functional programming and you'll learn more. um, so once we launch it, now we can actually just like train it. We can do something actually first. We can just like test the model and see if it's working or not. Let's just like uh, so, so let's just stick to this. First, we will create the model using the create function. We need an optimizer, and instead of using Optax optimizers, we can actually wrap the Optax optimizer here around the NNX optimizer that combines both the model and as well as the optimizer into the same kind of like optimizer, so we can actually simplify our code layer. We are using the metrics. Like this is a new actually library. This is a new actually feature that I really liked, which is like you can actually specify now. It's similar to how TensorFlow Keras used to do it. You can specify what are the metrics that you are trying to actually calculate, and then you can just like add them here. You can do accuracy. You can do a lot of other stuff. We can do actually accuracy, and then we don't need accuracy. C and stuff like that, and then you call it ACK and stuff like that. But we don't need accuracy. We are only interested in loss, and you can just like bash everything here, and then you can consume them later on in the training script. So here, like we will just like first of all try if the model is working or not, and see what is like the output of that model. And I forgot mesh. I forgot to define mesh. I think yes, I forgot to define mesh at the beginning. Let's actually just like define it first. Yes. I forgot the mesh, so it should be somewhere code. So let's just like define the mesh here. So this is the mesh that allows you to actually represent how many actually devices you want to train on, and what is like what are the axes that you want to actually focus on. First of all, there's like the batch axis when you are trying to create your own batch. I think we created it somewhere here. Yes. So this batch here will create a batch for you, a batch axis for you. And then we have like the model that is actually also like it's also like parallelized. So like in each GPU we have like the model that we created, and then each GPU will calculate the logits, and then we will combine the logits and weights from all these like GPUs into a single model, and then we can actually do the forward pass again. But for now, I think we can go up to 8 for this one. Let's go up to 8 so we can actually make it faster, I would say. Uh, okay, yes, like so we have 4. Yeah, it's 4. We have 4. We can just go to 4. It's 4 times 2, which is like a mesh that we are interested in creating. And then we can actually go run this again. is not defined. Did we actually lose? Oh, we did not run one of the scripts. We didn't run one of the scripts. Create casual mask. This one. Okay. Yes, it was just that function. We did not run it. Next time I should start running and then explain, so we don't do, I don't do this again. So it will use the function generate text that have a for loop of generating token one token at a time. That's why it's a bit like small. So this is the generated function or the text without actually doing any pre-training or anything like that. So like it's one upon a time. Gender is just like gibberish things, just like saying random stuff, which is does not make any sense. But it's just like only because we did not actually train it yet. So we need to go and train this model. So the first thing first, we can first of all we need to create to prepare our actually we need to prepare first like the metric, what is like the history, so we can actually keep it for later to actually do the just like to plot it later if we are interested in plotting it. And then we need to do something like this. We need to do a for loop. We will go through it one step at a time. So we will go to it one step at a time. So this is like a for loop of the number of epochs that we have. And this is a thing that you just like you can add just like to time your own like how much time does it require the CPU to go through each epoch. And then we will use the data set that we created using the script above. And we will just like do for batch in TextDL. And if you remember, the TextDL will take care of all like of just like taking or extracting the batch from the data set and just like providing it to us, like so we don't actually just like we don't need to actually worry that much about it. But now you can actually just like check if the batch is the same as like dividable by the number of like the number of or the batch is divisible by the number of like devices that we have, which is 8. If it's not, then we need to break. If it is, then we can actually go and continue. We will transform the input batch to jump to numpy arrays or GNP, JAX numpy arrays. And then we will prepare the batch to actually give it. And then we will give it to a training step using the training step function that we created, which can takes the model, the optimizer, the metrics that we are interested in. And then we will just like use JAXPut to actually put the device into like different like or to split the batch that we have into different devices. Like for example, if we have 256 of a batch size, we will split it on 8. So each do the math. Each let's do it. Like so it will just like do it will just like split it into 32 uh, mini batches per device. Per each TPU will take 32 mini batches and do the forward propagation or do the forward propagation. And the shredding, we are gonna shred only the batch access, so we can actually just like do the training step on it, and then we will combine it using like it will automatically combine it later. And then we will do like the metrics, so actually just like to add like the metrics that we have, and then just like print the step and stuff like that. And sometimes we also like see like we can see how the model is performing, so we can print the generated text. And then the final model, which is like it will just like print you the final actually performance of the model. If we run this one, it will take a bit of time, but we will be able to see how the model is progressing um, during the training and stuff like that. If you have any question, feel free to ask. If you don't have any question, feel free to enjoy. If you like to see code. Um, Thank you so much. But generally, we're just like it will just like load everything, and then we can actually do something later, which is just like okay. So it will start showing stuff right now. Let's see, let's see. Let's just like focus on it 100% and see like how it goes. It's not. It's still running. I can see like if you went back, yeah, it's still running. The code is still running. So let's see. It's gonna print anything for us. Just wait and see. I'm sure like there is still a bit of like the inability from. Let's just clean this one. Yeah, it's taking the whole RAM. The TPUs have a maximum of 330 gigabytes of RAM. But I'm not sure why it's not currently available in VM. It's fun, 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 fun. One of the cool features of Kaggle, you can actually just like prepare the datasets in Colab, and then you can actually upload your whole datasets to Kaggle, and then just like create an instance on Kaggle to actually use those TPUs and stuff like that. Which actually save you from a lot of pain from starting node servers and stuff like that, which is nice. Okay, so like this is the first loss or the first checkpoint, which is like the 200, and for each 200 epochs, it will just like take 119 seconds, 119 seconds, which is not bad considering that we are training a pre-training a transformer. But we can actually increase the batch size if we want to later. And then you can actually use better things. So this is the first time, the first generation of the model. If you remember, like the previous like text that we got was this, like once upon a time, and then just like kind of gibberish all long, just like everything is like kind of gibberish. But now we have a bit of like the model started actually learning the I'd say like it started referencing some of the stories inside the corpus. So like once upon a time there was a little girl named Tim and named Timmy. She loved to play, to play, to play, to play, to play, to play, to play. The girl was very mom. The little girl was a big little girl. Was a big little girl. Was very mommy. Well, anyways, it's like it's still a bit like learning stuff. The little girl was very happy, and it has like a bit of like you can see that it's learning some meaning in the process. So the total training will take around 200 or 8,000 and 200, but let's just like yeah, now she changed from little girl was Timmy now to Lily, and it's still it's still a bit not. I'm sorry. And said you can see now like the model started to learn how to create stories and stuff like that, which is actually fun to see. And you can see like now it's taking us only 60 seconds per 200 epochs since we are actually or 200 steps since we are now the data set is loaded to the shredded and is loaded. And this is just like for the first epoch, and then the second epoch the model will be a bit much faster, I would say. But for us, let's do something else. Let's just like let's stop or let's just like do let's just like try to wait for it. But we will need to wait for this code to run before actually running this code. Anyway, we can actually stop here. And then there's like actually the saving and everything later that you can actually use. But we can keep actually that until next time, I would say. Um, if you have any questions, feel free to ask. If you're not, I hope you enjoyed the session, and I hope I was able to explain some stuff that you've never seen before, or it's like that was a bit you were confused about. If you have any question, feel free to ask, and we can share with you like the notes that we are just like that we just shared. So let me just like update the code to the current code, and I will make sure to upload later, just like to add like the saving of the model and stuff like that once the code is finished executing. I hope you learned something new, and hopefully we can see you in the next episode, inshallah. Yalla, bye bye. Just like we will share with you first the code. I think it's in the shot. Yes. Let me check if there's any comments. Yes. That's the updated notebook. Let me see. Yes, now it's updated, so all the code is already there. Let me just go back and see if it still works using the link that I provided. Okay, I think it's working now, yeah. If you have any question, ask questions. If not, see you in the next one. Thank you very much for attending the session, and thank you very much for the people that are looking, uh, like just like looking at the recorded session. I hope you, if you have any question, feel free to reach out to me, either through ML Nomads or just like through like social media. This is like my tag is like Taha BSN, and hope to see you soon in the next one. Yalla, bye bye. Assalamu alaikum.